Yeah, so thank you for the kind introduction. My name is Klaus. I'm from the University of Regensburg, working in the group of Professor Jaroslav Fabian. I have changed the title a bit to be a bit more generic. So I will talk about these twisted graphene CGT heterostructures, but also about other twisted 2D material heterobilayers. So by now I think we all agree that 2D materials are highly interesting, and on top of that, for every 3D material we now have a 2D analog, be it metal, semiconductor, insulator, ferromagnet, superconductor, whatever you wish is available. And despite each individual material has highly interesting properties, we can combine them in van der Waals heterostructures where proximity effects play an important role. Okay, it's not working. Oh. So for example, if you look into such a tri-layer structure, then the effective Hamiltonian will not just be the sum of the individual ones, but rather it can be heavily modified by proximity effects. And the prototype material that one typically considers is graphene because it has a weak spin-orbit coupling. Actually, you can say it's absent, roughly. And it also has no magnetism in it. Now, one of the spin interactions that can be induced in graphene is the proximity spin-orbit coupling, as we have already heard today of. So, for example, if you consider graphene on top of TMDC, in this particular case it's MOS2, and if you calculate the band structure from first principles, you will find that the two individual dispersions are very nicely preserved due to the weak van der Waals interaction of the monolayers. And in particular, the Dirac cone is very nicely preserved within the band gap of the TMDC. However, if you then zoom in to the Dirac states, you will find such a splitting of the bands. And this splitting results from the proximity-induced spin-orbit coupling, which is of the Valley-Zeeman and Rashba type. So maybe I'll change this because my smartphone is maybe interfering. Okay. Yeah. Now, okay, thank you. Now, another spin interaction that can be induced in graphene is, of course, the exchange coupling. So, when you place graphene on chromium-germanium telluride, for example, which is a ferromagnetic semiconductor, you will find a very similar situation. The Dirac states of graphene are quite nicely preserved within the band gap, and if you then zoom in to the Dirac states, you will find such a splitting of the bands, which reminds us of the Zeeman splitting from an external magnetic field. But here is not an external magnetic field, it's rather the exchange field originating from the ferromagnetic semiconductor. Now the question is, why is this important? And I think today we have already seen why graphene physics is important, but still graphene has very nice spin and charge transport properties, and it can be used to perform spin logic operations. On top of that, when you, for example, combine graphene with a TMDC, it can be used as a field effect spin transistor. In this particular case, it's bilayer graphene on top of tungsten diselenide or another TMDC. It does not matter really much. And what is important here is the short rangeness of the proximity effect. So only the lower layer is proximitized. And on top of that, with the electric field, we can then switch the band structure. So we can effectively turn on and off spin-orbit coupling in the transport channel. And this can be used as a field effect spin transistor. Moreover, we have already seen that it can also be used to interconvert between spin and charge currents, such heterostructures. without the need of conventional ferromagnetic electrodes, we could actually switch between spin and charge currents. Now this is very nice, but still we would like to know if we can get another handle on this and somehow control the things a bit more. So we would like to have an on-demand control of these spin interactions and optimize the things for spintronic devices. And one way to do so is via pressure, external pressure. For example, in these experiments it has been demonstrated that the proximity-induced spin-orbit coupling can be drastically enhanced by external pressure. So what happens? If you place such a heterostructure in a pressure cell, you will effectively reduce the van der Waals distance, thereby the coupling between the layers is getting enhanced and also the proximity spin-orbit coupling is enhanced. And if you then do the magnetotransport measurements of such a system upon external pressure, you will find such a crossover from the weak localization into the weak anti-localization regime. If you then do the fitting of these curves, you will find that the rush per spin-orbit coupling can be roughly increased by a factor of 2 with an external pressure of about 1.8 gigapascal, which corresponds to a reduction of the interlayer distance by 0.3 angstrom, which is around 10% of the interlayer distance. And now the second thing that can be done is, of course, twisting. And the recent tight binding calculations have shown the following. So when you place graphene on tungsten diselenide, then the Waals-Zeeman spin-orbit coupling in graphene will follow this blue line. So we have this intermediate maximum at around 15 to 20 degrees of the twist angle, and it then goes to 0 at 30 degrees, which is due to symmetry. The rush per spin-orbit coupling does not show such a, say, nice evolution. It stays more or less the same over the whole twist angle range. And on top of that, the rush per spin-orbit field, this in-plane spin-orbit field, can be heavily deformed by twisting. So it has been shown that at 0 degree twist angle, you have such a tangential typical rush per field you would expect, but once you twist it to a certain angle, it can become purely radial. Now if you do actual DFT calculations on large supercells, you will find that the proximity spin-orbit coupling can indeed be heavily tuned, but the results do not completely agree with what the tight binding picture says, because, for example, this Waals-Zeeman spin-orbit coupling has here more or less a plateau and then drops to 0 at 30 degrees. So what is the consequence of this radial spin-orbit field? So if you do spin-charge conversion experiments, which we have heard of today, and you have such a typical radial tangential rush per field, then your spin density that you generate will be perpendicularly polarized to the charge current. This is known as this inverse spin galvanic effect or rush per Edelstein effect. No matter how you call it, it's the same mechanism. But if you then switch into this radial spin-orbit field, you can also tune the polarization of your spin density. So it can become collinear to the applied current. So with the twist angle, we have actually a knob to tune the polarization of the spin density. And now let me switch gears and come to the actual things I would like to present, which is the engineering of proximity exchange in graphene chromium germanium telluride heterostructures by twisting. So the situation we have is like this. We fix the magnetization of the ferromagnet and simply twist. On top of that, we can apply a transverse electric field to see how the things can be tuned. And what we do is DFT calculations on large supercells, and then we do the effective modeling of the low energy states. And the situation roughly always looks like this. So the Dirac states are nicely preserved within the band gap of the CGT. And now let me discuss on a specific example what is going on, which is the 30-degree twist angle structure. So the overall band structure we have already seen. The two different colors correspond to spin up and spin down. And if you then zoom in to the Dirac states for this 30-degree structure, you will find that the spin down bands are pushed to lower energies compared to spin up. If you place your Fermi level to this dashed line and you calculate the spin polarization that is on graphene, you will find it to be very uniform and negative. And the corresponding model parameters are the same for both sublattices and also negative. Now, where does this come from? If you consider perturbation theory, you would expect that the Dirac states would couple to these energetically closest spin-up substrate bands. However, if you would do that, then the spin-up Dirac states would be pushed to lower energies because energy levels that are coupled repel. However, this is not the case what you observe in the DFT calculation, and it's actually rather the coupling to high energy bands. And in particular, you will find such a pronounced anti-crossing of spin down Dirac states to substrate bands. And this is in fact pushing the spin down Dirac states to lower energies. Yeah, so the coupling is here. And another way to look into this is within the framework of the projected band structure. So this is again the full dispersion, but now decomposed into spin up and spin down manifolds. And the color code tells you something about the percentage of graphene within these states. So blue color means it's pure graphene, red color means it is substrate, and these rainbow colors indicate the coupling. And in fact, for the spin up case, you will find no coupling to these low energy substrate bands, while there is quite a weak coupling to these high energy levels. In contrast, in the spin down manifold, you find quite a strong coupling of the Dirac states to these high energy levels. And this is what pushes the spin down Dirac state to lower energies for this case. And now this is a summary of our most important findings. So for 30 degrees we have already seen what's going on. We have this negative spin polarization. Spin down Dirac states are pushed to lower energies, and these are the corresponding exchange parameters for our model. Now if we go to the 0 degree case, we find exactly the opposite. This is really remarkable. Spin up Dirac states are pushed to lower energies, and if you calculate the spin polarization, it's again uniform but positive on the graphene. So you can essentially reverse the proximity exchange by twisting. And what is even more remarkable is that at a certain twist angle, this 19.1 degree, you can actually realize antiferromagnetic proximity exchange in graphene, as we can see here, this very nice sublattice character of say positive and negative spin polarization on the graphene. And of course we did not only investigate these three angles, we did the full angle range scan, and what I summarize here is say the ferromagnetic and antiferromagnetic proximity exchange as a function of the twist angle. And what we can see here is that the ferromagnetic one can be tuned rather nicely from positive to negative values when twisting from 0 to 30 degrees. This antiferromagnetic proximity exchange arises only for this special twist angle of 19.1 degree. However, I have to admit that this antiferromagnetic proximity exchange is not very stable, so it depends really very sensitive on the atomic stacking that you employ in your DFT calculations. But still, it's a very nice finding. And of course, we did then also check what the transverse electric field could do. So in these two color maps, I again summarize this ferromagnetic and antiferromagnetic proximity exchange as a function of gating and twisting. And most important is, for example, if you look into this range, around 12 degree twist angle, then you can actually switch from positive ferromagnetic to negative ferromagnetic simply with the gating. So you can barely see this in this color map, but still this is a very nice finding that simply with the electric field you can switch the proximity exchange from positive to negative in graphene. Now why is this important? So this can be actually utilized for spin injection and transport. So when graphene is proximitized in the way I've shown, then the density of states will split up like this. And then the graphene polarization as a function of energy will follow this curve. And recent experiments by the Van Wees group exactly wanted to show this. So they did non-local spin transport experiments, which we have heard of today. And this non-local resistance signal depends on the injector, the graphene, and the detector polarization. And in this case, they were using non-magnetic gold electrodes, which means that the injector polarization is 0. And this also means that we have only 2 contributions left, which is the polarization graphene and graphene, this product, which simply gives you a spin-dependent background. And then this remaining product, P graphene, and the detector one. So the detector is cobalt. And now let's see if graphene really is polarized. This is what they measure. At 0 field, they measure a low resistance state, which means the graphene and the detector, the cobalt, are parallel polarized. At some field, the cobalt switches and we go to a higher resistance state. And at an even higher field, the substrate switches, which brings us back to a low resistance state. So when the substrate switches, the proximity exchange switches, and this means also the polarization in graphene switches. And this experiment very nicely demonstrates that we can use proximitized graphene for spin injection without the need of conventional ferromagnetic electrodes. And now in the remaining minutes I would like to talk about twisted TMDC heterostructures, and in particular the valley splitting, how we can engineer this. So what we consider are the semiconducting TMDCs, MOS2, MOSC2, and also tungsten-based compounds. And what is most important is this spin valley locking, which we have heard of today as well. And the important thing is, if you do optical measurements, then the plus K valley will react to a sigma plus polarization, and the minus K valley to a sigma minus light polarization. So if you do photoluminescence experiments at 0 external magnetic field, you will find that the PL peaks of the 2 polarizations coincide, right? Because they are energetically degenerate. Once you crank up the external magnetic field in the out of plane direction, you will find such a very nice splitting of these 2 peaks, which is known as the valley splitting. And this valley splitting follows this linear trace as function of the magnetic field, where also the G factor plays a heavy role. In this case of bare monolayer TMDCs, this G factor value is around 4. But still, if you apply a magnetic field of 8 Tesla, you get only a valley splitting of 2 millielectron volts. And this is where the proximity physics comes into play. So if you consider a tungsten diselenide on top of chromium triiodine, which is also a ferromagnetic semiconductor, then due to proximity-induced exchange coupling, a valley splitting of around 20 Tesla will intrinsically arise. So these are the data, and so this additional quenching of one photoluminescence peak for the sigma plus comes from the band structure simply, but still these 2 peaks are split. That would correspond to around 20 Tesla of external magnetic field. And this is of course why we considered this in DFT and checked what does the twist angle do, what does a gate field do into this, and the story goes like this. So if you start with a 0-degree twist angle structure, you can very nicely recognize the band edges of the TMDC here around the K valleys. These spin polarized in-gap states result from the chromium triiodine, which is also responsible for the quenching of the PL peak for one light helicity. And this is a calculation without spin-orbit coupling to really resolve the proximity exchange alone. Now if you zoom into the band edges, you will find a splitting of the conduction band edge and the valence band edge like this. The spin ordering is the same, and we characterize this splitting by a parameter BC and BB. And if you then go to the 30-degree case, you find that the conduction band splitting remains, the spin ordering remains, while the valence band switches sign. So we can again reverse the proximity exchange splitting in the valence band by splitting, which is similar to what we have seen before. And again, we did the full twist angle and gate scan. So the conduction band splitting stays more or less the same upon twisting, but the valence band splitting can be very nicely tuned from negative to positive in this linear fashion by twisting from 0 to 30 degrees. And if you look into this electric field and twist angle dependence, you can find that the conduction band splitting can be tuned in the range of minus 2.5 to minus 0.5 millielectron volts, while the valence band splitting can be heavily tuned from about minus 1.5 to 4 millielectron volt upon twisting and gating. And this has profound consequences for the valley splitting. So the most important result is here. So this is the calculated valley splitting for tungsten diselenide on top of monolayer chromium triiodine when we twist and gate. And the tunability is really giant. So you can go from 0 to 12 millielectron volts in the valley splitting by twisting and gating. These 12 millielectron volts correspond to an external magnetic field of 60 Tesla. And this is really a gigantic field. And this already brings me to the end of my talk. I hope that I could convince you that twisting and gating are two very, very efficient control knobs to tailor proximity physics in 2D material heterostructures. And with that, I thank you for your attention.
Questions?
In this TMD with proximity effect, do you calculate the anomalous Hall effect? Because if you have such a splitting, maybe...
Yes, one would expect that, right? But we do not calculate it.
No,
So right now we're at the stage that we have calculated all these heterostructures, applied the electric field, explained the mechanism, what is behind this reversal, let's say. But one could do that.
Yeah, because that could motivate, I think, the experimentalists to try, because that's kind of easy measurement. Right?
Yeah, sure.
It's very interesting talk. So you look at like the system that has very low DC, and actually chromium iodide has very low DC.
Yeah, and
right?
it's even more unstable, let's say, than
Exactly,
the
and
ZGG.
very sensitive to the oxygen.
Yeah.
So iron's germanium telluride becomes kind interesting candidate because it's also have like perpendicular lattice anisotropy. And recently people also try to basically interface with the tungsten diselenide as well. So that may bring up so basically like, you know, close to room temperature, you know, multiplicative effect, and that could be very interesting system to look at.
Yeah.
So regarding this TMD, I know some work they show that like on top of basically forming interface with other magnetic materials, you can dope magnetic, you know, elements, and that could also enhance Valley spin Waals splitting.
Mhm.
So do you think that would be interesting to approach using two different ways? So one is you dope to enhance that, and
Mhm.
then you can form the interface to further enhance Waals
Sure.
splitting.
Yes, I think so. Absolutely.
Thank you.
Yeah, hello. So it was a very nice talk. So I have a particular question for you. So like you mentioned previously, like the if you put any graphene, very low spin orbit coupling material in TMDC, obviously that will induce spin orbit coupling. Okay. So there are experimental and theoretical evidence that if you put a bilayer graphene on like WAC2,
Mhm.
that will actually change the spin orbit coupling of graphene from microelectron volt to millielectron volt, like 15 or 7
Mhm.
millielectron volt. Okay, and also you can tune the spin orbit coupling, and you can actually measure it by doing non-local measurements and other thing. Okay, so people have found both theoretically and experimentally that if you actually tune the perpendicular electric field from negative to positive, the splitting can change from for bilayer graphene from valence band to conduction band. Okay,
Mhm.
both like capacitance measurement or normal D measurements.
Mhm.
Okay, so my question is, what will happen for monolayer graphene? If you put monolayer graphene on WSC2, what will happen? Because for bilayer graphene, we can understand like the bottom part of the bilayer graphene is basically close proximity to the WSC2. That can actually enhance the spin orbit coupling for the bottom layer. But the
Mhm.
top layer, since there is a van der Waals distance between the top and bottom layer, so overall spin orbit coupling is basically small. So my question is, what will happen for the monolayer graphene? So can we act similar to the bilayer graphene? We can actually switch the like proximity induce
No. You
with a perpendicular field.
So
or
there is a small impact of the proximity spin orbit coupling upon electric field, but you cannot switch it because, in this sense, the bilayer structure is really completely
So
different.
yeah, I know. So what will happen with the field?
So you mean what happens to the effective parameters once you apply the electric
exactly. Experimentally for bilayer graphene, people have found like if you have some phase diagram of D versus density, like D is the field,
field?
what
Mhm.
I'm talking about, and N is the density. If you see the map near the if you the diagonal is the basically the Dirac point, okay, the
Mhm.
diagonal element. People have found some asymmetric dependence also. The asymmetry is coming from the spin splitting, okay.
Yeah,
So
sure.
what will happen for the monolayer case?
Yeah, so I guess what happens once you shift, say, the Dirac cone within the band gap, you can tune the
For
proximity.
monolayer graphene, there is no band gap.
No, within the band gap of the TMDC. So you shift your Dirac states within the band gap, and thereby you affect the proximity spin orbit coupling. This
How it will depend?
So we
Uh,
are running out of time, so probably we can discuss in the
Okay, sure. Yeah, we can just.
So thanks again